Um, Welcome to the 9 a.m. session. Oh, do you have my mic on? Good. My name's Scott Scher. I work for Ripple. The stuff I'm about to talk about has nothing to do with what I do at my day job. I very seldom do any type punning. I used to. I spent quite a number of years doing embedded development, and type punning is just one of those things that's unavoidable when you're doing embedded stuff. So it's something I care about. And when somebody said, you can't type pun that way, that's undefined behavior, my initial reaction was, okay, so what do I do? And they said, here, do this. Okay, but why? And so this, after a number of interactions with folks of that nature, I decided it was time to try to get a handle on this stuff. So this is the result of my research. I had help from a small number of experts, but the mistakes are my own. The correct stuff is largely due to the experts that helped me. So we're about to look at type punning. I don't have a monitor here. So we're going to talk about two things. We're going to talk about type punning. And so the question is, what is type punning? And I like the Wikipedia. This isn't quite the definition, but this is how they introduce it. And type punning is when you subvert the type system, is the way I read this. And I think that's a good definition. So we're talking about things that people would ordinarily encourage you not to do. And then, oh, sorry. There we go. Then the other thing we're talking about is C++17. When I first thought about this topic, I wanted to title it Type Punning Through the Ages. But once I started finding out how difficult it was to figure out what you can and can't do, I decided I really need to focus on just one standard rather than a collection of them. So we're only going to talk about what are the rules for C++17. Because we're talking about undefined behavior, you can't rely on what your compiler tells you. So the only place to go for information about undefined behavior, unless you're running UBSAN, is to the standard. So we're going to be looking at a number of quotes from the standard. And those aren't really from the standard. They're from that paper, which is pretty close to what's been finalized as C++17. It's not exactly there, but it's pretty close. We're also going to be talking a little bit about C11, which is the most recent C standard. And I don't actually have a copy of the C standard, but I did pull this paper off the web. So that's what I'm using. And I have compiled this stuff with Clang and GCC. Not all of it with GCC, mostly with Clang. So why do you type pun? What draws anybody to do this stuff? So the motivation for doing this is if you're doing endian conversions. It turns out that there are a number of folks who serialize their stuff to files by pretending that it's a bunch of unsigned char, shooting it out to a file, sucking it back in and expecting it all to work. That's type punning. If you operate on any opaque type, and opaque types happen to be things like pointers and floating point numbers, the standard says nothing about what the internal of a pointer or a floating point number is supposed to be like. So once you start digging around inside of a pointer or a floating point number, you're doing type punning, whether you know it or not. So what are the risks? There are a number of risks. None of it's portable. Because when you're type punning, you're relying on a local representation of some piece of information. And that piece of information, the way that information is stored, can change, not only from processor to processor, but from compiler to compiler. And when you change your compiler flags, it can change. So this stuff is not portable in the most serious possible way. It's fragile for the same reasons we were talking about before. And it's hard to maintain because generally you're doing something that's a little bit off the beaten path. So when somebody comes in to do the maintenance on this stuff, they're going to say, what in the bejesus were you up to? And if you're there to answer the question, you can tell them. But if you're no longer in that job, they're going to be guessing unless you've left voluminous comments and they bother to read them. The stuff is bug prone because we're going to see just how much undefined behavior lurks around the corners of this stuff. So we're going to focus on trivially copyable types, and we'll get to what those are. The reason being that many of the techniques we're using they're defined only for things that are trivially copyable. So if you're not using a trivially copyable type, when you're type punning, you're in even more danger. Definitions. And I should pause for a second. If you have questions about stuff that I'm saying, I am hoping this will be an interactive session. So hold your hand up, interrupt. I'll try to repeat the question. So we're going to be talking about things like undefined behavior, and I think it's a good idea to start with what do these things mean? So we're going to say, I've said use trivially copyable types. So what does the standard have to say about what a trivially copyable type is? And in order to figure that out, we have to go back a few levels in the definition. And we're going to start with what an object representation is. An object representation is an array of bytes. And then inside of that array of bytes, let's see. There we go. So the value representation, inside of that, the value representation is the set of bits inside of that array of bytes. Okay, everybody with me? So you got a bunch of bits in some number of bytes. And then for a yes, Ben?
Is the implication there that there might be some unused bits in your object?
Yes, so Ben's bringing up that there may very well be unused bits in the object, and that is 100% correct. So for trivially copyable types, the value representation is the set of bits. So if that's not true for your type, it's not trivially copyable. The standard library provides a type trait that will allow you to see whether your type is trivially copyable or not. So if you're type punning, be smart to use that. Yes, Vinny?
How does it know?
Next slide. Perfect setup. The question was, how does it know? So the standard, because it's hard for it to know the stuff, the standard infers what a trivially copyable type is by looking at this set of characteristics of the type. So it looks at the definitions of the move and copy constructors and assignment operators. And if any of those are user-defined, then it knows it's not trivially copyable. If it has a non-trivial destructor, it knows that it's not trivially copyable. There are a couple of other things, and it's not just the outermost object, it's all of the objects all the way down. Yes?
Jason and I found, Jason and I found that trivially destructible. What you said about user-defined applies to basically all the special member functions. You just have to mention them, and it's not trivial.
Yeah.
It doesn't matter. They can be empty, but they're still not trivial.
Right. So Ben's point is very useful. In order for any of these special members to be non-trivial, all you have to do is mention them. So if,
You have to give them a if you use equal default
Yeah. So if you give them an empty body or whatever, then they're non-trivial. Virtuals are bad. Not in general, but if you're trying to make a trivially copyable type, then as soon as a virtual shows up, it says, no, this is not where we're at. So a bunch of things are trivially copyable. Chars, arrays of things that are trivially copyable. Structs, generally. You can have protected and private sections and things that are trivially copyable. They're still just fine. You can have unions. You can have arrays of structs or arrays of unions. All of those things can be trivially copyable if the things that are inside of them are also trivially copyable. The place where you can't go is you can't have a reference. References are not. Here we have a user-supplied copy constructor. That means this is not trivially copyable. And here's a virtual. So this one also is not trivially copyable. So we're done. We've beaten trivially copyable into the ground. Yes?
So I would expect that another property we like is standard layout. What's the relationship between trivially copyable and standard layout?
Yeah, so the question is the relationship between standard layout and trivially copyable. I'm not an expert. We will be looking at standard layout, the properties of standard layout a little bit later on in this session. My belief, which is not to say that I'm an expert on this, my belief is that if it's if it's a standard layout thing, object, that it is also trivially copyable. But there are things which are trivially copyable which are not standard layout. One of the constraints, I think, for standard layout is that you may not have sections that are private, and with trivially copyable, it is allowed to have a private section, for example. So the other thing, we're going to be getting into undefined behavior. So let's see what the standard has to say about this stuff, because that's really, that's the only thing we can be talking about. The standard is the thing that says whether something's defined behavior or not. So there are actually a number of kinds of behavior that the standard talks about that are interesting. People talk mostly about undefined behavior, but there are other things to consider as well. So the first one I wanted to mention is implementation defined behavior. So this is stuff that depends on the implementation, and your implementation is obliged, according to the standard, to document what it will do. So if you were to go and look in the standard, and I encourage you all to take the time to do that, it's hard to read, but it's not impossible. And just because you interpreted it one way doesn't mean that's what it really means, but you're often right. So I encourage you to go ahead and make the effort. But it will call out specifically if something's implementation defined. And then you're supposed to go to your implementation and say, how do you behave? So there are a couple of examples here of things that are implementation defined. The number of bits in a byte, and that surprises some people. I worked with the DSP for quite a number of years where there were 32 bits in a byte. That's just fine. The standard doesn't mind that. Let's see if I can get there. All right. So the next one is what atomics are lock-free, if any. That's up to your implementation. So that gives you a reasonable intuition for what implementation defined means and why it's used. So beyond that, there's unspecified behavior. Unspecified behavior, I think, is really interesting because when behavior is unspecified, it is always explicitly called out in the standard as this behavior is unspecified, which is kind of backwards to me, but if it says if it doesn't mention it in the standard, there's a different rule. The standard can say this is unspecified behavior, and it generally will say here's the range of acceptable behaviors. Your implementation is not obliged to document what it will do. But the standard will say here's a range of acceptable behaviors, and your implementation might do any one of these. So here are some examples of unspecified behavior. I'm turning around because I don't have a monitor up here, and I'm working on the same information you guys are working on. So the order of evaluation of arguments and using function call syntax, that's up to your implementation, and it doesn't have to say what it's going to do. And where the memory for an exception object comes from, that's all up to your implementation, and your implementation doesn't need to tell you how it does that. Now we're on to undefined behavior. So there are two different ways in the standard to get undefined behavior. There are a number of places where the standard explicitly calls out that there's undefined behavior, but the primary way that undefined behavior happens is if the standard doesn't say anything. If the standard is silent on the topic, then that's undefined behavior. It is literally, there is no definition. And the other choice is when the program uses an erroneous construct or erroneous data, that will be explicitly called out as undefined behavior. So you can get to undefined behavior in one of two ways. One is if the standard doesn't tell you that you can do it. So implicitly you have no permission to do things that it doesn't tell you you can do. Or it may say, this is undefined behavior. You can get there either way. So here's one. When you, I'll mention that the things that are in the square brackets, you can use those to reference a section of the standard. That's how, there are chapter numbers and stuff in the standard, but those move around over time, and the square bracket things are supposed to stay constant. So if you do searches for the square brackets, that'll get you to the right section, and then there's a paragraph. So that square bracket expert, that's a reference to a section in the paper that I was referring to. And then that's paragraph 4. So the consequences of overflow or underflow of assigned integer, that's undefined behavior, and that's called out explicitly. Any kind of a race condition, doesn't matter. And the standard also defines what a race condition is. I don't want to go into that, but it does say explicitly, if there's a race condition, that's undefined behavior, and with good reason. One of the things that was interesting to me is that an access to the non-active member of a union, and we'll talk a little bit about how a union member gets active, but an access to a non-active member of a union is usually undefined behavior simply because the standard doesn't say you can do it. It's silent on that, and therefore you infer that it's undefined behavior. Wish this weren't jumping quite like that. Okay, so like I mentioned earlier, undefined behavior can change over time, not arbitrarily, but if you change compilers or change compiler flags. In particular, compiler flags have a huge impact on what happens. And that's because if you change your optimization level, your optimizer may take advantage of something being undefined and saying that can't happen. So the standard does say list a bunch of expected behaviors for undefined behavior. The one that it doesn't mention, I'll say this one first before we go through the other ones that are in the standard. The most likely thing to happen when you run across undefined behavior is your compiler will do exactly what you hoped it would do. So you are unlikely to see, when your code has undefined behavior in it, you're unlikely to see any negative consequences. I'm not saying you won't. I'm just saying it's unlikely. So your implementation is allowed to document, if this is undefined behavior, this is how I'm going to behave. And it is allowed to terminate either the compilation process, I suppose it could terminate the linking process if it knows how to do that, or to terminate its execution. That's all fine. The other thing it can do is ignore the situation completely with unpredictable results. This is what your optimizer takes advantage of. So it can generate smaller or faster code. So when undefined behavior gets in your way, it's because your optimizer or compiler is trying to do you a favor. Your compiler will generally not intentionally reformat your hard drive or make demons fly out of your nose. So the question is why and people have made the point, the reason I'm mentioning those is those are all things that people have brought up as the potential consequences of undefined behavior. But your compiler is not going to do that. And the reason it won't is that there is no economic incentive for your compiler vendors to do anything like that. They want you to use their tools. The reason that undefined behavior is when it does behave funny for you, the reason that it's behaving funny is because they're trying to do you a favor. They're trying to make your program run faster or be smaller, or both. So my take on undefined behavior is that it's everywhere. If you think about the definition of undefined behavior, that's a huge space. It's all of those things that the standard doesn't say. So the likelihood of your program containing undefined behavior is very, very high. Just as an example, how many multi-threaded programs have guaranteed no race conditions? And there may very well be some, but I don't think there are very many of them. And so my inclination is that pretty much any multi-threaded program has undefined behavior. So I hope some of you are old enough to catch the Dr. Strangelove reference. My take is no, that we don't just go, nah, I'm a believer, everything's good. I think it's worth understanding what's undefined behavior and staying out of the way. So now actually to the meat of it. Yes, Ben?
Sorry, just one comment. It's not probably relevant to this topic. What you're doing can't happen in context program, but I think compilers are required to diagnose undefined behavior if you're evaluating a context program.
Yes, Ben's pointing out that if you're evaluating in context per context at compile time, then, so it's not obliged to do this if you have a context per function that is executing at runtime. But if you have a context per function that is being evaluated at compile time, it will not contain, by the time it's done, it will not contain any undefined behavior. The compiler will only do things that it knows how to do. So thank you, Ben. That's an excellent point. The easy place to start is what happens when we cast away const. So the standard is extraordinarily clear about this. You can cast away const all you want. That's just fine. Don't mutate a const anything unless it's marked as mutable. So if it's a const object with a mutable member, that's fine. Change it all you want. If it's just a const object, the standard says that's undefined behavior. Now, that's not to say you can't get away with it, because we've talked about, the compiler isn't enforcing any of this, and it may very well do what you want. But it is undefined behavior to change that value. This is straight out of the standard. So the standard's being about as clear as it knows how to be. Don't change those consts. And I think it jumped. Let's see if I can get back to that. Yep, okay. So, for me, I wanted to look at a motivation for why would the standard care. And when you modify a const, well, let's start with what are some of the optimizations that an optimizer might want to do? Well, if an optimizer sees that something's const, it knows that it's not supposed to change. So if you change a const value, the optimizer or compiler may have cached that value previously, and so may not see that change. So there are very good reasons for this rule. The rule of don't change the const makes your compiler, gives your compiler an optimization point. So this is one where if you don't follow the rule, you are likely to get slapped because your stuff won't behave the way you want it to. I'm not saying you will be slapped. I'm just saying that it's a greater likelihood. But there's sort of a way around this. This is new in C++ 17. It's called standard launder. And it's not something that people talk about a lot because it's pretty hard to use, in my estimation. But you can use it. So what we've got here is a const with two, or a struct with two const members. And we're newing it. And then we're doing, on the next line below, the yellow line with the new, we're doing a placement new over the top of what we just did. Yes, Arthur, I'm going to be corrected. Good.
You're not going to be corrected. I have a question about this that I don't know the answer to. You might be getting to this, but I notice not only are you putting a new object in there, you're doing it without destructing the old object.
Right.
Now, the old object has a trivial destructor, but even in that case, is it okay to skip the trivial destructor and just not call it? Yeah.
Okay, so the question is it okay to skip the trivial destructor when you do the placement new? And I'm not an expert, and if I'm not seeing any experts hold up their hands to say, I know the, oh, okay.
It is okay, you can skip a trivial destructor, that's kind of the...
Okay, we've been assured by an expert that you can skip the trivial destructor. So thank you. Thank you. I'm relying on you guys. So what we're doing is we're doing a placement new over the top of a pre-existing object. And so we have undefined behavior when we're accessing the members of that object because we've modified const values. See if this will work. Okay, so what we can do is we can, at the place where we're doing the access, there's nothing you can do at the place where you're doing that second placement new. There's nothing you can do according to the standard to improve that situation. What you have to know is that I, as a programmer, know somebody screwed around with that const value. If you know that may have happened, then you can use standard launder at the site where you're accessing the thing that may have been messed with. So this is very hard to use correctly. But it's here. And I guess one other thing worth pointing out is that you'll notice that those other two accesses that are not through the standard launder, those two accesses remain undefined behavior. So launder doesn't clean the whole thing. It can provide something that's clean. So if, see if I can advance through here.
Use the make mouse pointer as much as you show.
Well, yeah, okay. So, well, so you can save the pointer that's returned by standard launder. And if you always access through the pointer that came from standard launder, then you're golden. Okay. So you can either go straight from the response that launder gives to you, which is that pointer, or you can save that pointer and go through there. And the compiler and optimizer will say, okay, we know that const is not necessarily there. Otherwise, you're on your own. So I think standard launder is hard to use correctly. If you're relying on that to get you out of trouble, that's a hard road. So my suggestion is if you can possibly avoid it, don't mutate const things. I'm going too slowly. Thank you, Eric. So let's talk about pointers. This is a damp pointer, one of those new kinds of pointers. So I want to start out with using an invalid pointer value is purely undefined. So anything you do with a pointer, you need to be careful with it. Thanks. It's bouncing. Where is it going? I think I'm going to have to give up on this and get stuck.
Undefined behavior.
Yeah. All right. I know where that is. We know where that is. Okay. So manipulate your pointers carefully. So the type punning that is very clearly talked about in the standard and is well defined is converting between pointers and integers. What's that? I think I'm good. So pointer to integer conversions are well defined by the standard. There are some constraints. But the mapping in both directions is well defined, and it is the exact nature of the mapping is implementation defined. So the form of the integer that you get out of that pointer is up to your implementation, but it's guaranteed to make the round trip. So whatever that integer is, when you turn that back into a pointer of some kind, that pointer has, if you didn't mess with the integer in between, you get the same pointer back. So it's round trip capable. So here's an example. A uint pointer t, that's one of the two types that the standard provides for you to do this conversion. That's basically just an integer that's big enough to hold whatever the representation of a pointer is. So we're turning a pointer to doubles into an integer. IP is an integer. And we're using that integer over here. We're doing addition, integer addition with the plus I. And then we're casting that back into a double pointer. And I think this is, Eric is telling me this is undefined behavior.
I'm pretty sure because the representation of it as uint putter is not guaranteed to be equally as sequential as when it's a pointer. So you need to do the addition while it's a pointer.
Okay, so Eric is saying he thinks this is undefined behavior. I'm not going to disagree with him.
Probably some in here who are better at the standard than I am, but
Yeah, okay. So I'm not going to disagree with him, not an expert. But this was something that I thought might very well work.
That's a good description. It might very well work.
Okay. So I think
behavior, but it might very well work.
yeah, so I think I've just heard a second to agree with Eric that this is undefined behavior.
Maybe implementation defined the exact behavior of conversion between pointers and integers.
Yeah, Yeah, I would say implementation defines both. It'll give you back a pointer that compares equal to the original pointer, but then you go and do stuff with it.
Yeah, so my reading of the standard, which is I'm not an expert, was that as long as the integer to pointer conversion gives you back a pointer which would be valid.
Right, so the problem here
Oh, I see.
is you're doing the addition and then you're dereferencing it, but because you do the addition on it as an integer
Yes.
rather than as a pointer, there's no guarantee that that's going to be a valid pointer that you're then dereferencing.
Okay, yeah, right. So I will absolutely agree with you that there is no guarantee that after the addition that the pointer that you get back is a valid pointer. I completely agree with that.
Can I ask you something?
Yes.
Okay, now I'm gonna ask some questions. I might be wrong, so don't laugh at me, but uint pointer t lets you convert any integer on the platform to an integer that's large enough to hold it?
No, so the question is, well, so let me see if I can clarify this.
Okay.
A uint pointer t is an integer type.
Right.
It's an unsigned integer type that is big enough to hold an integer representation of a pointer, of any pointer on the platform.
Okay, next question. What is the size of a float on a 32-bit platform?
Well, so we're not talking about floats. We're talking about pointers.
Okay, what's the size of a double on a 32-bit platform?
A double. It is implementation defined, but in either case, we're not talking about floating point numbers. We're talking about pointer to integer conversions and back.
But it seems like the integer is 32 bits while the double is 64 bits in size.
But there's no double here.
It's right up there.
There's a pointer to a double. So what we're doing, the uint pointer t is operating on p, which is a pointer to a double. So we're converting a pointer to a double into an integer. We're not converting the double into an integer. We're converting the pointer to the double into the integer. And I can see I'm not going to get anywhere close to the end of my slides. So
Could be a void star too.
yeah, so my hope was, and the experts that I work with didn't call me out on this, but that's not just, that's my responsibility. I think this is as close to well-defined behavior as it can get, assuming that after the addition, the returned pointer is a valid pointer that you've recalculated. That's not to say that it's, okay, I'm getting a thumbs up from over there. So we're type punting, we're skating on the edge this whole way. So what the standard guarantees to you is that if you do that round trip, don't mess with the integer. You just turn it into an integer, turn it right back into a pointer. The standard guarantees that's okay. So in my particular implementation, when I did that computation, again, what I'm doing is I'm messing with a pointer. I'm taking a pointer to a double. And I'm turning that pointer into an integer. And I'm adding an integer to that pointer, which happens to be the size of a double. So I'm indexing. And then I'm converting that integer back into a double. And people are making faces. Can't say I blame them. So those are optional types. The compiler says, or the standard says you may or may not have those in your implementation. If there is no integer type big enough to hold that conversion, then it will certainly not be provided. And the integer representation of the pointer might not be the same bit sequence as the pointer itself. The standard encourages people to make that something that would be sensible to someone who understood the underlying pointer. But it's just encouragement, it's not a requirement. And in terms of choosing between int pointer t and uint pointer t, I would get very uncomfortable using an int pointer t, because if it, an assigned pointer just doesn't make any sense to me. So moving on from integers, if you have an initialized value representation, there are a list of a bunch of different ways you can access that value. And all of them in the standard, this is in basic LVAL paragraph 8, they all contain the word the dynamic or something or other about the object you're referring to. And there are a bunch of those. And at the very end of the list, you get 3 to work with that have no relationship to the original object. You get to look at it as though it's a char, an unsigned char, or a standard byte. Yes, Peter?
The idea is to get just standard byte in some future life.
Okay, so...
Or some future
yeah.
timeline
Yeah.
that spawned off 10 years ago, or 20 years ago.
Yeah, so Peter's point is that the goal for the standard is to move away from unsigned char and use only standard byte as the way to access this stuff. So, but for right now, this is what the standard says. So that's how you can access something that has a determinate value. So if you have something that is an indeterminate value, how do you access that? So to start out with, we need to talk about what an indeterminate value is. And it's something that's been brought up into existence either through, because you have an auto thingy on the stack, or because you brought it from the news store. And so it has, you don't know what is inside. So we've got some examples of things that are indeterminate values. Note that we're not at file scope. If it's at file scope, it gets initialized to a well-known value. But if it's just being generated locally, it has these things, because they don't have constructors that initialize them to particular values. They have indeterminate values. So that class, for example, as a member that's not getting initialized, that union, all these things, they have uninitialized values, or indeterminate values. So there's a section of the standard that talks about how you can access the contents of indeterminate values. And it says specifically that you can't get there unless you're using an unsigned char star or a standard byte. So those are your choices. What I think is interesting about that is that if you're accessing any kind of a value, whether it's been initialized or not, you can get to it through either an unsigned char star or a standard byte. Okay? I'm not seeing any disagreements. That's reassuring. One of my experts did warn me, you have to be careful how you've got your pointer. I won't tell you how to be careful how you got your pointer, because I think that's too confusing for me. Not for you, but for me. That's hard. So we've got a piece of code here where we're going to be accessing the least significant bits of a pointer. I've got a pointer, and I have the unsigned char const star const. That's a pointer to my pointer. Okay? And we're going to roll that pointer. That pointer is going to walk across. And we're going to look at just the 2 least significant bits of that pointer as the pointer changes. And at least on my implementation, this is not portable. On my implementation, this is what I got out. So that worked. And I'm not seeing anybody saying, that's undefined behavior. So I think I'm safe. So here's what happens. We're moving on to a general reinterpret cast. What happens when you convert a pointer to something very different? And you can convert any pointer to any other pointer type. And accessing through that pointer, so the conversion itself, the compiler's not going to yell at you. You can go ahead and make that change. But accessing through the pointer is very well likely to be undefined behavior based on a number of issues. So is the representation valid? Yeah. It goes as fast as it goes. Yeah, okay. So what we're about to talk about is this last line, strict aliasing rules. The strict aliasing rules have been with us for a long time. They were introduced in C back in the mid-'80s, I think. But before we can talk about strict aliasing, let's talk about aliasing. So what we've got here, the sum twice function, it takes pointers to two integers and it adds them twice. And I want you to think about what you would expect this to do. And I'm calling that function down here below. And what I'm getting out is a 6. Okay, this all makes sense? Now we're going to get into aliasing. The second two lines in my example, we're passing the same pointer in. The top function has no idea. I mean, it sees pointer A and pointer B. Those may point to different things, but it doesn't have to. So as soon as we call the function with pointer A and pointer B as the same value, we're aliasing. And the compiler is obliged to do the right thing. So that's aliasing. And you will see that we do get two different answers based on whether we're aliasing or not. So is aliasing a problem? Well, okay, what it does is it slows your compiler down because code runs fastest in registers. Pointers and references, you can alias through references. Pointers and references both operate on memory. They work on memory addresses. So if a memory location might be aliased, then the compiler is obliged to either write to memory or read from memory if that alias might have been used in the interim. So that's aliasing, and that's why it's not your friend most of the time. Sometimes you really want to do it. But when it can happen, your compiler will slow down. And so here are the strict aliasing rules. There are a set of object types through which the compiler is obliged to do the right thing. The strict aliasing rules list those. They're all here. I'm not going to read them out. They're in the slides. So maybe I can go a little bit faster this way. You'll notice that in the end, you're always allowed to access through a char, an unsigned char, or a standard byte, just like we saw before. So the reason for the strict aliasing rules is so your compiler can run faster, so that there are fewer pointers that may be aliasing that are forcing it to go back to memory. That's the point. So here's an example of typical type punning that is a strict aliasing violation. So what we're going to do is we're going to swap the halves of a 32-bit integer through that pointer. So we're taking an object, which is a 32-bit thingy. We're making a 16-bit pointer so we can access that. And we're swapping those things around. The compiler is, this is strictly by the standard. This is undefined behavior. And by the way, when I did this in Clang, it worked just fine. no problems, within O3. So the optimizer saw what I was up to and did me the favor of doing what I hoped it would do. You can disable the strict aliasing rule on most compilers. But if you do this, your code will probably run slower because it has to go to memory more often. I will mention that, since we're talking about making your code run more slowly, you can, in C, you can tell your compiler that you can make a promise to your compiler, there are no aliases to this pointer. And that terminology is restrict in the C standard. And since many C++ compilers also support C, many of them have extensions where you can do something that has the word restrict in it. So that you can say, this section that I'm really worried about, I can guarantee to you that there are no aliases. Please optimize this the best you can. But then the onus is on you. Don't lie to your compiler. So, regarding pointers, signed to unsigned, that's well defined. UN pointer T between pointers and integers, that's well defined. Eric tells me what you do with that integer is risky. Not going to argue with that. And then accessing through a standard byte char or byte star or an unsigned char star, that's okay. Let's talk about unions. Oh boy. All right, let me talk quickly about unions. So there is a way that you can type pun with unions, but it's not probably what you think. So there is in the standard an escape clause regarding unions, that if you have inside of the union standard layout structs, and this was the point you were getting to, or may be related to the point you were getting to earlier. So standard layout structs inside of a union, and it's also a standard layout union. Then you're allowed to access the common initial sequence if there happen to be things that are in common between those structs, and they're at the front, then the standard specifically allows you to do that. What's a standard layout struct? The definition, you can find it there in the standard. It's a long definition. But the point of it is to constrain the data so that it's shareable. That's the reason that they care about that, because they're trying to create a type which is shareable between languages. And you can identify it with this static assert. So the compiler will look at this type and tell you whether it's what you want or not. So you can avoid actually trying to drive through the standard E's. This is an example of a common initial sequence in a union. So I've got a nil, a bus, and a car. And what you'll notice is that they have a common type T at the front. So in my example, I'm setting my vehicle as a bus. I'm setting that value. But when I access for that assert, I'm not accessing through the bus. I'm accessing through T, which is the null type. So I can find out that there's a bus in there. And the standard says that's okay. What it doesn't say is that you can do anything else funny with a union. So with a union, you've got an active member of the union. And it becomes active when you assign to it or do a placement new into it. That's how it becomes active. And that's the active member of the union. So you can access the active member of a union if you have standard layout structs and there's a common sequence. You can access that. any access to a non-active member union other than what we've just talked about, that's undefined. So, meantime, over in the C standard, C11, there is this exact paragraph. This is footnote number 95. This is not normative behavior, but the paragraph itself is extremely clear. So I think that if a compiler vendor chose not to follow the advice of this non-normative note, they'd be in a lot of trouble from their users. So I think there's a lot of power in this non-normative note. This says that in C11, if you do type punning through a union, you're on good ground. That's the way I read it. So, in C11, again in non-normative text, so it's not binding by the standard, but it's very clear. Access is well defined. And my belief is, I'm not talking about what our standard says. My belief is that if you have a compiler that supports both C11 and C++17, your compiler is likely to give you the C11 behavior simply because it's too much work not to. They've written that code. They know how to make that work. I'm not saying that it's, the letter of the law is that accessing through the so, no guarantees. Let's see if we can race through unrelated object types. I've got 5 minutes. I think these are unrelated object types. I think there's very little to do with a submarine and 3 polar bears. So we're going to do an exercise. What we're going to do is we're going to, for good reasons, we're going to take an integer, which will be a NAND payload, and we're going to turn that, we're going to wrap a float around that integer. So this is the NAND with a payload. That's something that the floating point IEEE standard, whatever that number is, this is something that's well described. So this is the function we want to write. We want to put the contents in there. And we have to use type punning. So we're going to start with a strict aliasing violation. This is the easiest one to do. So we're going to take cargo, which is our UN32, that carries our payload. We're going to OR into our cargo the stuff that has to go at the front that turns that cargo into a NAND. And now what we're going to do is we're going to return that as a float using that reinterpret cast. The reinterpret cast is not undefined behavior. That's just fine. What is undefined behavior is that return of what's pointed at. Next option is a union. We've already talked about unions. What we're about to do is we're going to drop cargo into our union of a UN, the combined UN float. So we're dropping, well, we start out by initializing that with either the positive header or the negative header. And then on the ret I or equals cargo, we're going to OR in the cargo. And that's all fine because we're operating on integers. And now we're going to access the float in the union, and that's undefined behavior. Now we're going to use memcopy. So what we're going to do is we've got our separate float for return. We're going to do the bit manipulations over here on cargo because it's easy to do that on an int. Now we're going to memcopy that into the return value, and then we're going to return that. Now the question is this undefined behavior? This is absolutely, if you look on the web, this is the answer you'll get. The web tells you, do this. Okay? So if you look at what the standard has to say about this, again, I'm just a programmer. When I'm dealing with the standard, I am struggling. Okay? But the standard does explicitly say that if you're copying the underlying bytes for the same trivially copyable type, that this is okay. This is a swell thing to do if it's the same type. And then there's silence. So when I read that, my inclination is to say that this is undefined behavior. But I suspect that if I talk with somebody who's actually in core, they will say that it's not undefined because memcopy uses unsigned char as its access method. So I think this is really skating on the edge. Nevertheless, this is widely promoted as the way to do it. And I wish that if this is what the standard wants to promote, that they would come out and say it.
Write a proposal
Yeah.
and use
I-
divide.
Yeah, and okay, and I think that proposal may very well be coming. Thank you. So hopefully I'm not too far over time yet. So the last choice, this is the one that I'm pretty confident doesn't have any undefined behavior. Is that if you just use unsigned char star or std byte, and the reason I didn't use std byte in my examples is my Clang doesn't support it yet. That's the only reason. I would have been using std byte everywhere if it had worked. But using an unsigned char star, pretty confident this is not undefined behavior. So those are my 4 examples. And I should have silenced my phone, sorry. That was not intentional. So C++ folks care a lot about how fast will something be. So I went ahead and disassembled all 4 of those examples. When I counted instructions, I did leave out, there was a common header to all 4 of them where they all did an assert. They did the same assert, threw that out. That's not relevant. So in terms of the changes in the type punning methods, and I'm compiling with Clang on Mac OS set to -03. So this is maximum optimization. And I'm not saying don't follow the strict aliasing rules. The strict aliasing rules are absolutely in play. Nevertheless, what Clang produced for me was 9 instructions for the one with the unsigned char, 8 instructions for all 3 of the other examples. And for all 3 of the other examples, despite how different they looked in the code, the exact assembly instructions were the same for all 3 examples. So I think I need to jump to the end, which is probably good because I was about to embark on some more undefined behavior. So let's jump to the summary.
The compiler terminated your app.
Having to go over time.
Yeah. So here's the summary. I was very proud of this one. So avoid modifying non-mutable const values. Consider the effects of possible pointer aliasing. Be aware of that whether you're type punning or not. Be aware of the strict aliasing rules. When you're punning with pointers, prefer standard byte star or unsigned char star. For punning pointer math, there was stuff that we skipped that you can look at the slides later on. Pointer math is hard to get right even if you leave it as a pointer. So if you're doing punned pointer math, there may be good reasons for you to do that as a uend pointer t. So I would encourage you to consider doing your punning pointer math as a uend pointer t, and then and then argue with the committee if you don't get the answers you want. And I think the real key to this is that avoiding undefined behavior is hard. Thank you very much for attending.